Let's talk about the slant asymptotes in this video. It's the non-horizontal line, y equals mx plus b. So we will be graphing some linear functions. It's an asymptote of the graph of the function if f of x approaches this mx plus b, this line, as x increases or decreases without bound. What does that mean? Well, that means you're going to have a graph. Let's say that you have your x-axis, y-axis, and say that you have your horizontal axis. I'm sorry, not horizontal. Let's say we have a vertical asymptote right here. And then I'm going to sketch a slant asymptote. Maybe like that looks like this. This pink line is called a slant asymptote, and the graph will look like this. Okay, hold on. We're going to have a graph that is in between these asymptotes, and x gets really big. The graph will get infinitely close to that whole slant asymptote, but it will not touch it. And to the left end, okay, as x gets smaller or x decreases, this graph will get infinitely close to that slant asymptote, but it will never cross it or it will never touch it. Okay, so that's what it looks like. And we will have some graphs that has a vertical asymptote and a slant asymptote instead of a horizontal asymptote. So that's what the picture looks like. So let's talk about how to find it. And I need to tell you when it exists, because it doesn't always exist. It only exists when, let me go ahead and highlight this for you because this part is going to be important. A rational function in simplest form has a slant asymptote if the degree of the numerator is exactly 1 greater than the degree of the denominator. So here's an example for you. You may have a function that has f of x equals x to the third power plus 2x over x squared minus 5x. I just made it up. But look at the degree of the numerator. What is it? That's 3. Look at the degree of the denominator. That is 2. So you see how 3 is exactly 1 bigger than 2. So this function will have a slant asymptote. Another one, g of x. What if it has 5x squared minus 3 and then x plus 5? Let's compare the degrees here. Degree of the numerator is 2. What about the degree of the denominator? It's not written, but it's really x to the first power, right? Because the top is 2, bottom is 1, on the denominator and the degree of the numerator is exactly, it's bigger than the degree of the denominator by exactly 1. So we have 3, 2, 2, 1. These two functions will have a slant asymptote. But how about this one? N of x for no slant asymptote. If you have a function that looks like this, 5x cubed plus 4 over x to the fourth power plus 3, just made it up. Look at the degrees. The top degree is 3. The denominator is 4. You see how this function will not have a slant asymptote because the degree on the numerator is not bigger than the degree in the denominator. In fact, this will have a horizontal asymptote of y equals 0, but no slant asymptote. For any graph that has a horizontal asymptote, there's no oblique or slant asymptote. Okay, so if it has a horizontal asymptote, it's not going to have a slant asymptote. Alrighty, let's go ahead and do some fun example. I'll do example 1 and maybe 2 in this video because I think these will be a little bit shorter. Example 1, we are reading graphs this time. The graph of a rational function f is shown below. They got the intercept, asymptotes and graphs and everything graph for us. So what are we doing? We are finding some important parts of this graph. Assume that all asymptotes and intercepts are shown and that the graph has no hole. Now look, if they have a hole, it's going to look like this. They're going to have like an open circle. Okay, we don't have a hole here. So use this graph to complete the following. I see the graph. I see. Okay, what are we doing here? First, find the x-intercept and the y-intercept. Okay, so x-intercept first. Maybe may have more than one, who knows? So where is the x-axis? X-axis is this right here. Is this touching the x-axis? We know it's not. We know it's not going to touch it because the way they graph this dotted line, do you guys see? This is a dotted line, right? This is y equals 0, okay? And this is a horizontal asymptote. When you plot these, when you graph these with dotted lines, these are asymptotes. So what we are saying is, as x gets infinitely big, as we go to the right end of this graph, the graph will get very close to this dotted line y equals 0, but it will never touch it. Okay? So x-intercept, none. There's no x-intercept. The graph, the blue graph, is not touching the x-axis at all. Okay? Because the x-axis is its horizontal asymptote of y equals 0. Okay, how about the y-intercept? Is this graph touching the y-axis at all? If it has one, it's got to be just one y-intercept. So if I'm looking at the y-axis, oh, right here, you see, guys, right there, it is touching the y-axis at this point right here, and that is 1. So y-intercept is at 1. Moving on, they said write the equation for all vertical and horizontal asymptotes. We already found the horizontal asymptote. I'll say HA is y equals 0. How about that vertical line? What about that vertical asymptote? We have a vertical line at, this is 2, this is 3, 4, 5. So this must be x equals 4. So we have a vertical asymptote at x equals 4, and there's no other dotted line, so that is it. Now let's do the domain and range for the last part. Domain is going to be everything except for the vertical asymptote, because remember, vertical asymptote is when that function is 0 in the denominator. So using the vertical asymptote of x equals 4, the domain is going to be everything to the left of that positive 4, but also everything to the right of that positive 4. But don't draw a square bracket. Make sure you have a regular parenthesis because it cannot be 4. The graph is not going to touch x equals 4. And there's an asymptote right here. Now, how about the range? Look at the picture for me. Does it go below? I mean, I can see that it's pointing up forever. So y value, the high end is going to be positive infinity. It's going to go up forever. But will it go down? Not really, right? The lowest point it is trying to go to is at y equals 0. So the range is going to be 0 to positive infinity because it doesn't go below y equals 0, right? The blue graph doesn't go below the x-axis. It's just above the x-axis. So we say the range is from 0 to positive infinity. Let's do one more reading graph problem. Example 2. The graph of a rational function f is shown below. And as I can see, I have two vertical asymptotes. The first vertical asymptote is at x equals 3. And the second vertical asymptote is at x equals negative 2. Okay? How about the horizontal asymptote? We see another one at y equals 0, right on that x-axis. So I think that's what part B is. They wanted you to find the vertical asymptote. I can say x equals negative 2 and x equals 3, just reading the dotted lines. And the horizontal asymptote is at y equals 0. All right, let's see if this graph touches the x-axis at all. X-axis is this. Well, look. Oh my goodness, I saw it. I was going to say, no, it doesn't touch the x-axis at all. But as I was following my x-axis, at this spot right here, do you guys see? This spot right here at 2. It actually crosses the x-axis. So we found the x-axis, okay? And remember in class we talked about how the graph can never cross the vertical asymptote, but it can cross the horizontal asymptote because the horizontal asymptote is just about the right end and the left end behavior. It doesn't have anything to do with what the graph is doing in the middle. So that's what happened. Right in the middle, like this middle piece right here, it touched the x-axis at 2. So I'm going to say that there's an x-intercept at 2. Okay, how about y-intercept? Let's find that one too. Is this graph touching the y-axis at all? I'm following my line, and right there, I see it. I see it's touching the y-axis at -2. So hey, y-intercept is -2. So we are good with part A and B. Let's talk about the domain. Now remember, for the domain, you always just look at the vertical asymptote. Okay? It's going to be everything except for -2 and +3. It helps for me to draw a number line. I like to draw a number line. So here's my -2. Here's my +3. Open circle over there because we're not allowed to have those. But we're going to have all the way to the left from -2, everything in the middle, and everything to the right of 3. So here's the domain, okay? -infinity to -2, comma, union. The one section in the middle is -2 to 3, union. And the last section all the way on the right is going to be 3 to +infinity. So that is the domain of this function. Because we had, as you can see, 3 pieces of graph separated by 2 vertical asymptotes, right? Now let's talk about the range. Look at the picture for me. Obviously, this picture is going down forever. So we're going to say -infinity. And will it touch the horizontal asymptote? And it actually did. And the middle piece alone covers the entire number line, really. This piece only covers the line, covers from -infinity close to 0, and the one on the left is going from 0 to +infinity. But, you know, the middle piece covers everything from the -infinity to +infinity. So just by looking at the middle piece alone, the range is going to be all real numbers. It touches everything. It goes everywhere. So range is -infinity to +infinity. So that should be enough for reading graphs. Please come back and watch the other videos on graphing rational functions. I have about 6 more videos on graphing, and I go over one example at a time in each video.